Hi, I'm Dave Robinson, Chief Data Scientist at DataCamp, and I'm going to be doing a screencast where I analyze a dataset in real time that I've never seen before. I'm really excited to do this because I love exploring data. I love grabbing a new dataset, finding things out about it, making some visualizations. It's one of my favorite parts of the job. And I think people that are new to data science, it's really worth showing how much can be done with some code and with some experience in R, and show what a typical process of exploring a data set looks like. So I'm really excited to show my process and show this as an example of a data analysis. So I'm going to do an example from Tidy Tuesday, which is a really exciting project set up by the R for Data Science online learning community. So every week they release a data set that people can analyze, make visualizations of, draw conclusions from, and I'm going to be analyzing the most recent version, which again I've never seen before. The only thing I know about this is it's about college major and income, and that it's based on a 538 article. So the data is here, right? I'm going to be downloading this, learning things from it in R, making some visualizations, and showing if I were just curious about this data set, what would be the first things that I discover about it. So let's see. I'm definitely going to come back to this data dictionary where we find out what each of the columns mean. But first, I'm probably going to want to grab it into R. Now, if this were a large data set, if it had lots of different files, I would probably be cloning this repository, but it looks like there's just one CSV file here called recent grads. So a nice trick that I'm going to do is I'm going to read this directly into R. So here is the file, looks like a CSV file, and I'm going to click raw, and I actually get a URL here. I'm going to be able to read this directly into R without actually cloning the repository. That's nice because I could share this code to someone else and they could use it themselves. So I've got an RStudio project here, and I'm going to work in an R Markdown notebook. I almost always work in an R Markdown notebook. And it's really good because I can kind of combine my conclusions alongside my data. So I'm setting up a new chunk here, and I'm loading up Tidyverse package for exploratory data analysis that gets all my packages. All right. Before I start, I'm going to share that this is not a tutorial. I'm not doing this in order to teach you how to use R and understand each step so that you can follow along with it. If it were, I'd be going slower. I'd explain things more. I definitely would have prepared in advance. Here I'm showing, I'm going to work at close to my regular working speed and explain what I'm doing as I go, but give a sense of what kinds of alleys I'd go down, the process of what I do if I wanted to write a blog post about this. So I am going to be probably working pretty quickly, definitely more quickly than I would if I wanted to teach this. So I'm going to create a setup chunk where I need to read in my data. What was it called? It was called recent grads. And I can, with the read CSV function, read directly from that URL. That was pretty easy. Here's my data down here. 173 rows. All right. I get the impression from the name of the project that it's that every one of these rows is going to be a college major. So let's look at this data a bit better. I'm going to pipe it into view. Almost always the first step when I'm working with a new data set. All right. So we have some kind of ordering and rank. Every major has a code. This looks like an integer, but it's really a category. Major, all right, all in caps. I wonder where statistics is. That was my major. Statistics and decision science. Sure, cool. We've got what looks like a total number of people, number of men, number of women, categories of majors. That's good. Get to kind of combine them together. Share of women, I'm going to guess, is women divided by total. Sample size, I'm gonna have to learn what that is because I would think that would be this. I would think of that as being total, as being samely as total, but it must be a random survey from within these people. I'm gonna quickly jump back to the data and take the data dictionary and take a look at that column. Full-time. So it's used for earnings. So we're gonna be looking at economic guide to picking a college major, typical salaries, and it looks like while we have these totals, we also have a sample of people that were asked full-time year-round asked for their salaries afterwards. Okay, good to know. All right, so sample size. We have number employed, number full-time, number part-time. That's not out of the sample size. That looks like it's, and full-time year-round. All right, that looks like it's out of the total, just based on the sizes of the numbers, 16,000 and, okay. And then we have number unemployed, and what's probably more interesting, the unemployment rate. Wow, a lot more variation than I would have expected. So we got like 17% unemployment rate in nuclear engineering. Seems maybe not where I would have expected out of the data. All right, and median percent 25th and 75th. I'm going to guess this is salary range. Yeah, looking at the numbers, it looks like salary range. So they don't share mean, which makes sense. Salaries tend to be log normally distributed. So you, that is, have a really long tail like of large values. So it makes sense to look at median. Oh, so I can make like a plot with, that'll be pretty neat. I'll get to see the low to the high to the median. I haven't read the 538 article this is based on. I kind of want to show what I would do with this data set brand new, but later we'll check out the article and we'll see if they have some of these same instincts for plots they'd create. College jobs, non-college jobs. Number with a job requiring a college degree, number with a job not requiring a college degree, and the number that are in low wage service jobs. So I'm really switching back and forth, kind of guessing what things mean and checking out the documentation. Different people might have different processes here. All right. All right. So I almost always start by picking a couple columns that are most interesting to me and making a visualization of them. So I'll tell you, I can't... see, I'm really interested in salary. I think that's the thing out of here that we're definitely going to come back to. Things like how popular the major are, also somewhat interesting, but I'm really interested in salary. So I'm going to look at median first. All right, so I'll take a look at recent grads. Now that I've picked something I'm interested in, I'm going to want to make a plot. I want to know the distribution of medians. Are some of them really cheap, some of them low earning, some of them high earning? I'm going to make a plot. I like to set my theme to a non-default ggplot2 theme usually, but I'm going to make a plot of median. When I look at a distribution, I want to see a histogram. All right, so we see the most majors make a little over 30K. I'm going to guess this is money made right out of college, but I don't have a median earnings of full-time year-round workers. Maybe not. All right. It might share a little bit more about it here. Whether it might not be full-time work. This might just be median college major. All right, and then we have a couple really high earning ones. We're later going to look at, are those just like really the kind of colleges you want to have a lot of money from, or are they make a lot of money, or are they low sample size? It might be a lot of variation. We'll take a look. All right, that's a histogram. I want to divide it down by something. I want to know by major category. So I'm going to throw major category on the x-axis in a box plot instead of a histogram. Box plot is really good for comparing a couple of distributions. This x-axis is no good. I'm going to coord flip this so that I can actually read the x-axis. Well, that's pretty neat. And I'm actually gonna do one other trick to tidy this up. I'm going to put the major category, I'm going to reorder it by the median column. So I'm going to sort it so we get to easily see the ordering of majors from lowest earning to highest earning. So notice I was using major category. There are 173 majors. I can't necessarily show them all in one graph, but I can definitely look by category. So I'm always going to have the question, does it explain a lot of the variation? Oh, and it looks like it absolutely does. It looks like psychology and social work tends to have the lowest earning graduates. That looks like a median of around, I don't like this being on a exponent. I'm going to make this a $sign. So this is a, you always have a choice when you're making graphs. Do you early on optimize just for explore, make some really quick plots, and later on you make them presentable. Sometimes I'm usually focused on making them just quick plots, but some things I really care about, and I like this to be dollars. So psychology, social work, $30,000 median, and engineering, closer to $60,000 median. So we definitely see a difference. STEM is at the top. STEM and business, engineering, computers, business, physical science, social science, life science. All the sciences, I think all the sciences near the top. Generally, we see a spectrum from STEM to liberal arts. So that would be one of the early conclusions I would make. This can actually be, later we might, this is already a pretty solid graph in terms of final conclusions we could draw. So another way we could have shown this would have been to do median. So I might have wanted to just say, if you don't care so much about the distribution, and especially if you're showing it to a less technical audience, I might have said instead of showing the full distribution, I'm going to group by major category, summarize to find the median, and then plot. Well, it'll be almost the same graph. So I'm going to actually just copy and paste. But change this to geom call from geom box plot. So this actually shows, this actually will show the median salary for each person. I'm going to need to add one more. There it is. And it brought back my reordering. So those are two ways we could have shown very similar data. Bar plot of the medians, box plot of the, so notice the box plot gives strictly more information. So I kind of like that about it. All right. What is up with this outlier? I really want to find out what that is. So let's actually look at what are the highest. So this I'm going to say is, as I go, I kind of give each section of graphs titles so that later I can turn them into a blog post or report. And I'd say, what categories of majors make more money than others? And I'm going to start a new section. And this section, I haven't saved yet. I'm going to save this as college majors. All right. And yeah, I'm going to actually ask a new question, which is, what are the highest earning majors? And with that, I'm kind of going to also ask, can we trust these individual values, or is it a matter of sample size? So anytime I want to say the highest earning, I'm going to use a range. So a range in descending median. And in this case, I'm going to grab just the columns I care about, the major category, and the median. Right. And we see it's petroleum engineering. Oh, that actually sort of makes sense to me. The kind of people that work in geosciences, go work for oil companies, can really make a lot of money out of that. One thing that's strange to me, I see 75 and 73. Here they are. Okay. So I see that the only outlier we have is petroleum engineering. People presumably going to work for oil companies, making this much money, and the rest of the people falling into this category. Right. I'm actually going to also add our percent, I think it was P25 or P25th and P75th. Select in this case is optional. It's just so I can kind of focus on the top few for what's relevant. All right. Okay. This is, so what we're seeing here is wow, a whole bunch of engineering areas. I'm going to make a graph out of this. People might be interested in what are the highest earning majors. And I'm going to tell you one of the, let's see, you can't put 173 rows onto a graph. I'm going to look just at the top 20. And what kind of plot am I going to use for this? You kind of have an option between a bar plot and a dot plot. I'm going to actually make it a dot plot and say major, median, geom point, and code flip. We're going to code flip a lot of things because we often have text on the x-axis. And I'm also going to reorder a lot of things. So I'm often going to be grabbing that line where I reorder a category. Oops, I want to reorder the major category. Oh. Reorder major and plot major. I had to get the category straight. Awesome. One problem with the dot plot is it's not going to start it at 0, whereas a geom call always does. I'm going to add expand limits y equals 0. We did a coord flip, so it's actually the y-axis to 0. All right, and we see this tells easily the top 20 majors. And I'm actually going to use another aesthetic. I'm going to say color equals major category. And this means I'm going to be able to really get that conclusion that it's mostly engineering. I can probably fit 25 onto this graph. I cannot, because that gets another category and it's not really worth the effort. All right, so petroleum is an outlier and everything else is mining, mineral engineering, all these other ones. All right, court reporting is the highest law in public policy. That's neat. While dot is a start, but I'm also going to want to show intervals. Here I have the 25th and 75th percentile. An error bar is perfect for showing that. So I do P 25th and Y max equals P 75th. And here we go. So that actually gives a much better impression, is a lot of these overlap. And it's this we sometimes, I've heard it called a TIE fighter plot. I don't know if it has a name, but a dot with bars around it. We could have used a bar with error bars around it. The reason I use the dot is mostly that a bar with error bars makes me think it's uncertainty in the value. And it's really worth noting, this is not a credible interval. This is not a confidence interval. This is not that we're unsure what the median is. This is about this is the range of salaries. So we learned some really cool things, which is 75. The 25th percentile of petroleum engineering is higher than the 75th percentile of most other careers, and with the exception maybe of metallurgical, nuclear engineering, astronomy, and astrophysics. Nice. And we see other things like that. Some of them have different variation. Court reporting, really thin interval. Most people court reporters, it looks like they make. I guess that's about $50,000, and it's very similar across all of them. So actuaries also small variation. Later we might look at like what's it called, the interquartile range, the 25th to the 75th, and look at how that varies. For now, this is a solid plot. I'm probably going to keep that one if I was to turn this into a blog post. The last thing I'm going to do to clean things up is that majors. It's bothering me that it's all caps. I might keep doing this for other analyses. I'm going to use a great function called string to title that I think will turn this into title case. Great. This comes from the string-r package, str to title, and that it's so much better to read. All right. Later I would go about and give these better labels. We might get back to that later when we're polishing our results, but let's keep this momentum going, keep exploring. What are the lowest earning majors? Once I realized that I want to ask these two questions, I refactor my code slightly. I now know I want to change this to be major. I want to have a processed version where here we go. I want to have a processed version of the data where I do this selecting, I do this mutating, and this rename all these changing these columns, and I didn't say, and then I do head 20 right here before I graph it. The reason I like that is now I can take a new graph where I'd say tail 20, and a otherwise very similar graph. So these are the lowest earning majors. A lot of them are they're different categories, so we see they're kind of widespread. Library science, various kinds of psychology. It's hard to see an absolute trend. We saw that on the box plot as well, that a lot of these kind of overlap. And we see the medians tend to be between 20 and 40K. All right. That's cool. That was kind of diving into particular majors instead of general major categories and distributions. And we look at the interquartile range. While I'm looking at this, it's really important that we look at sample size as well. They mentioned that sample size is how many people do we have that we're actually basing our earnings off of. If some of them are really low, we're not going to want to trust those too much. They might have a lot of variation. We don't actually have a confidence interval here. They didn't give that to us, so we can't say exactly how uncertain we are, but we know we want to take that with a grain of salt. If they only asked 20 petroleum engineers for their for their salaries, we're not going to want to trust that. So I'm going to make one more graph. Before I do that, I take it back. I'm going to grab sample size out of the recent grads table. Oh wow, some of them are based just on some of them based on just 3. All right, yeah, so that we're definitely going to want to be careful of making too many conclusions from that. And I'll show a way we might go about some ways we might go about fixing that. So let's look at late major. So if I take majors processed and if I arrange, we have the processed version here. Right, I'll see this. There's a graph I like to make. It's, I believe, called a bland Altman graph, where you put a total on the x-axis and your variable of interest on the y-axis in a scatter plot. So I'll show what that means. I'm going to put sample size on the x-axis, and I'm going to put median salary on the y. And I'll tell you, I know right away if I put sample size on the x-axis, it's got to be a log scale. And what this shows me is there a lot more variation in our low numbers, in our low sample sizes than our high ones. And it looks like there generally is. We can always get a little bit more data with this stuff. I'm going to put the color on I'm going to put the major category color on the major category on color, so we can maybe get a little more sense. Too many categories for that to be useful. Drop it. But I am going to drop in I do geom text, way too many points. I'm going to library GG repel. Remember that if I were teaching, I would probably show the graph that didn't work first, but I want to give a feel for my own workflow, where I usually would immediately think of geom text repel. And major vjust. Can I do? Yeah, I can. No, I can't. I don't think there's other options in geom text repel. I get to set a force. Oops. It's label equals major. The force will control how far do things. Text repel is never going to work on. That looks terrible. I was thinking not of geom text repel. That's why I was trying to label every single point. That looks rotten. I meant to do check overlap equals true, where this is not going to show every point. It's going to show as much of the text as it can. This is built into ggplot2, and I love this feature, check overlap equals true. vjust equals 1, hjust equals 1 is going to put them a little to the below and to the left of each point. That's a pretty solid graph. All right, so we can see up here, there's absolutely variation in the common ones. Everything from nursing economics on the higher end to psychology, biology on the lower end. And as particular majors. But we're seeing actually back here, we really kind of notice this scattering, this kind of, this effect comes from low sample sizes are going to have a lot of variation. They're also, honestly, they're going to be less interesting to our readers too. It is interesting that petroleum engineering makes a lot, but is it but if you have so few majors in mining and mineral engineering that we only get this small sample size, and I didn't look at the actual total number of majors, but I bet it's low too, I think we can kind of just drop a lot of these out. They're not going to be that impactful for our readers. We could still include petroleum engineering, or we could not. What I'm doing right now is I'm picking a cutoff. I'm going to say of majors that have at least a sample size of such and such. And I kind of notice I want it to be higher. I want it to be in this to be higher than this area where we have a lot this upper end of ones that might be a lot of variation. I'm going to set 100. I think that might let us graph all of them on one. It means all of them are really meaningful ones that we might know someone who'd majored in that. I'm going to see what this graph looks like. If it's before I do head 20, I'm going to say filter sample size greater than 100, 50, 100 or 50. I'm going to try 100, and I'm going to see if all of them fit. This is always going to be, there's going to be some judgment calls. There's always going to be questions, people saying, oh, why did you show only that many? Can't fit 100 on one graph. Good to know. If I can't fit 100 all in one graph, I'm going to change the threshold to 50 and do head 20. All right, and I liked 100. I kind of liked all the really common ones. Yeah, you could go back and forth. You've got to be really careful. If I were doing a statistical test, I would not have done this kind of slicing, or would have been very careful to do it in advance, because you can definitely p-hack. But if you're showing a visualization, it's more about show the things your audience is interested in, and here they might not be interested in the most obscure majors. So I kind of like the feel for this graph. This might be what I'd show, and what I would do, I'm going to put this in now so I don't forget, is say, I like to title the graphs of the question. That definitely your mileage may vary. Majors, and I'd say subtitle of majors earning with I'd say top 20 majors with at least 100 graduates surveyed. So that way I can be sure when I'm communicating, oops, not the x-axis, that's going to be the title. When I'm communicating, that people understand the limitations of this graph. I can throw in a dollar format. Sometimes I clean as I go, sometimes I don't, polish as I go. And here I can, so close, I would say median salary of graduates. I'd probably go back and add a little bit more detail to some of these. I like to drop the x-axis. It's obvious these are majors. This looks better. That's a pretty solid graph. Oh, and I forgot to say the bars represent the 25th to 75th percentile. Really important to say these are not confidence intervals. These are ranges. All right, that's a solid graph. All right. I'm going to move on. We've looked at the highest earning majors. I would probably go about doing the same thing for the lowest earning major. I'm going to move on to the next topic because I think I'm happy with the amount of time I've spent on that. And as the next step, I'm going to look back at the original data and say, what's the next question I'd like to answer? I showed sample size before, but I didn't show total. That's a pretty interesting one. I'm going to mention, I'm going to start with most common majors. I sometimes do my analysis out of order. I'm going to go back to something that is more of an introductory topic, which is most common majors, and show how we can get some interesting details out of that. I'm going to look at recent grads. And I'm going to say, yes, most common majors and most common categories are two separate questions. So first I'm going to start with most common categories, because that's the level that most people understand in engineering versus business. So if I group by major category and I summarize for median, sorry. I actually just need to count, not to group by and summarize. I want to know the number in each. And I'd say descending, I can do count sort equals true. This is a very good bar plot. This I'd want to, I got to do count weight is, we have to weight by the column of the number of people, the total. Get rid of the plot. What I was doing there was figuring out how would I say number of people majoring in it. And I'd say I want to count major category, but weight by that total column. All right. And now I know, what is that? 1.3 million are business majors. This is a good bar plot. This is a classic bar plot. Just like I don't even really need to look at it as I go. I can kind of just say coord flip and throw that mutate. I'm always be reordering. Always be doing FCT reorder to reorder your major category by your N. N is a terrible name, so I'm actually going to go about saying number of total graduates. Ideally, I'd go back to the data and look at is this in 1 year? Is this in whatever? Yeah, so that's a solid, this is a solid graph. I learned a trick from Julia Silge, my former colleague from Stack Overflow and co-author of Text Mining with R. The trick I learned is you get a bar plot with kind of a boring looking colors. I like to throw in a fill equals major category and then drop my my x-axis. Pardon me, drop my legend. So look at that. You just add kind of a rainbow effect. A lot of our plots do this. It's a very easy trick, but the truth is I'm really into it in terms of how it makes the graph kind of interesting to look at. So now we're seeing the most common are business, humanities, liberal arts, education, engineering. Our highest earning one comes in at 4th, and it looks like yeah, some of the less common ones: law, public policy, agriculture, natural resources. All right, that's cool. We did already look at a similar bar plot for highest earning major categories down here. If I turn this into a, well, there's not highest, so there's all of them, yeah. So we're really noticing like there's a lot of variation in how many people take them, but mostly the categories are like engineer, STEM, and everything else, kind of when it comes to median. All right. So that's the most common major categories. If I wanted, I could also plot the most, I'm keeping this because it's, you generate a lot of bar plots early when you're understanding an analysis because you really like to understand, like, you want to look at, let's look at every number, or in this case, every category. So here, instead of count, I'm going to do, I believe we already did this earlier, but, oh no, I remember now. I wanted to look at arrange in descending order of major, most common majors. This is actually more similar. All right, this is more similar to this later step of processing. So now I realize I've learned I really like this data set, majors processed. I'm promoting it. If you read one to a post-processing step, and while I do, I'm going to drop out this select because I need all the data. This is me realizing that there's some data cleaning I want to do early on. This is pretty clean data already, but there's some data cleaning I want to do early on. So I'm going to do it right after I read in the data. That way I can always work with it. Heck, I'm going to go ahead and ensure that I do always work with it. Yeah, if you read my blog post, it would look like the first that I made out of this, or out of a similar data set, it would look like the first thing I did was read in the data and process it, but that's not true. The first thing I do is explore. Later I realized, oh, there was some pre-processing that could be done, like reordering and changing strings to titles. But now that I've realized I always want to do string to title, I improve that a little. I move that up a little bit. And that makes some things pretty handy. I can reorder my major by total and then get a major total graph. Here I do want major category on the in the fill aesthetic, and say top. What were the, so up here I would write text like what were the what major categories, e.g. engineering. See, I'm already starting to think about like what could be drafted here. Engineering, psychology, business, were most common majors. And then I'd say, since there were 73, we're not going to show them all. That's the kind of thing I might say here. And here we go. The most, nope, that's definitely not right. I said major categories, majors processed, total, arranged, descending total. This should have psychology up at the top. I did head 20 because I arranged in descending order of, I have to rearrange in descending order of total. That was the 20 highest earning while showing the totals, which is quite misleading. This is the graph I wanted to make, ordering by top 20 most common majors. and we combine it with their category. There's a lot of categories for colors. I might just toss this if I decide to put this in the final product. But I see it's like psychology, business management, biology, various kinds of business we've seen. All right, these are some really common majors. On this x-axis, I would like to throw, pardon me, it's actually a y-axis with a code flip. I would throw in labels equals comma format instead of dollar format. That's going to look pretty swell. 100,000, 200,000. Yeah, I like that more than scientific notation. Good stuff. All right, so those are some common majors. All right. One more thing while I'm looking at totals is we have two columns right next to it. Men and women, male graduates and female graduates. All right, so I think that's really worth showing some let's look at breakdowns and let's look at let's look at breakdowns and let's look at most skewed in each direction. So that's actually before we get to money. I take it back. Let's do it after we get to money, because people are going to want to read about money early on if there's a report or if there's a blog post. So let's say, how does gender, I know I'm going to want to say how does gender breakdown relate to, how does gender breakdown relate to typical earnings? Okay. First, we got to know, what is gender breakdown? What is it like? What how do majors differ between the number of male and female graduates? So I've got men and women here as totals. That means I can do something pretty handy. I can plot that on a plot that looks just like this, but breaks it down into male and female by doing a gather. I'd say I gather into gender and number. And then which two columns do I want to gather? Men and women. This means I actually want to have, send up at the end. Boy, that's handy. Select major, gender, and number, the columns that I want. Here it is. Here we have gender, men, and number. And so here I've gathered that column into men, and later there's women. And that's really, really handy, so that I can do, I need the top 20, the 20 most common majors. All right, I'm going to do arrange by descending total, head 20, gather after that, and then I'm going to do major, number, fill equals gender for my bar plot. So fill equals gender is pretty handy for if I want to show this kind of breakdown. I'm grabbing my my mutate back really quickly. Mutate. Lots of ordered bar plots, lots of mutating on them. There's my graph. So when I saw that graph earlier of geom of most common majors, and I had this question in my mind: how do those break down? It's really interesting for the most common majors for sure. So notice that some, like business management, split about down the middle. Some, like nursing, far more women graduating. Some, like computer science, far more men graduating. Elementary education, more women. So these are of the most common majors. How do they break down? If I was showing, I might not show that earlier graph. I might have shown just this one, especially if the topic of the article was about gender breakdowns. Now that I've looked at that, I really want to know what the extreme values at either side are, what majors have the most, are shifted most towards men or women. I don't need to gather for that. I need to mutate. I need to, or did they already add a column for, oh, share women. They already added my women divided by total. So some, like, this is petroleum engineering, are 12% women. Some, like, this is maybe astronomy, are more split down the middle, 53%. But that gives us what we would need for this graph. I'm first going to quickly take a look at the sorted version of this graph. I'll arrange in ascending order first. We have some, like, I'm going to pipe this to view because otherwise it's unreadable. Military technologies records 124 men graduating and no women. Although a lot of these, let's see, construction, mineral engineering. So a lot of engineering tends to have very few women, around 10 to 20%, and women for a lot of the engineering. All right. And at the side of the most women we have early childhood education, communication disorders, medical assisting services. All right, so we have special needs education. We kind of see a lot of health and education. Notice as soon as I started looking at these, instead of looking at the individual major, which is very specific, I started looking at major category. That tells me I probably want to aggregate by major category. What I'm going to do is I'm going to group by major category. And I'm going to say, we definitely could look at the most skewed majors, but it's probably more interesting to divide it by category and say group by major category and summarize men equals sum of men. I'm going to use actually a different verb now that I'm thinking about it. I'm going to summarize at. What I want to say is for total men and women, I want to sum those categories within major category. This summarize at is super nice for, I like to add up a few things. And then I learned that agriculture, natural resources, we saw that food science had NAs. That's disappointing. I'm going to add na.rm to my summarize, and I at least get the rest of those people. All right. So now that I've done that, I've got to add my share women column back with a mutate. Women divided by total. And group by, summarize, arrange. Really common pattern. Descending, share women. We're probably going to make this into a bar plot. I just wanted to show that, look at the table first. So group by, summarize, mutate, arrange. There we are. We generally see health and education, about 80% women. Engineering, computers, mathematics, more like 25 to 30% women. So this looks like our variation. All right. You know what's interesting about this is that now that we have this, if we're going to look at salary and how it relates to gender breakdown, we're probably going to want to add something about salary to this table. That tells me I was wrong to do a summarize at. Summarize at is great for doing a couple of columns, but not if we want to add some columns that aren't sum. So if I say men, sum of men, women, sum of women, I finish my aggregation with total is sum of total. So far, same thing. Oops, I forgot the NARM equals true. Boy, that's I'll change my approach. I'll do filter not is NA total. Oh, that looks great. There was a filter at the start to remove that one field. All right, and while I'm at it, I'm going to start with median salary. Median of median. This is a median of medians, which is like, okay. There are other ways to measure to do this. We probably should weight the medians by the sample size. Should I do that right now? Yeah, I'm going to do that right now. Honestly, there are a few ways to go about this, and this is not the fanciest way, but my big concern when I do a median of medians is there's going to be a few of your high variation ones that really drive it. We're really more interested in the common ones anyway. Okay, I'm just going to weight the medians. We could spend more time on that, but I actually want to weight it by sample size. This is a weighted median, so the really high sample ones are going to get more, have more effect on the outcome. All right, so I definitely messed up something there. Sum of sum of median divided by sum of. There, much better. Oops. This is a weighted mean. The other thing was not. It was, yeah. This is much better. Okay. So this is our medians. These are median salaries. We arrange by descending share women. This, I think everyone's going to be interested in these two columns. I'm going to save this as by major category. We're doing, I like to name things that are summaries by major. when I create a variable, haven't been doing this, but I like to name the chunk according to the object that it defines. And yes, this is a bit better. So I'm going to look at by major category. All right. I've been speaking very fast, and I only recently noticed that. I don't mind coding fast, but I'm going to try and speak a little slower going forward. So I want to compare these two. We could absolutely graph. We could just graph one of these two columns on a bar plot, but the comparison between them is interesting to us. Already, my eye is looking, trying to say, are the ones with a greater share women, lower median salary, vice versa. So I'm going to take this, and I'm going to do compare share women to median salary. I put share women to the x-axis because I'm going to be very careful to say this is about correlation, not causation. We absolutely cannot say share women causes low salary causes share women. We cannot say that. But the way we're often going to think about this is do ones with a high share of women end up with lower salaries? That's why I chose the x and the y axes that I did. Looks to me like a negative correlation. I'm usually going to want to expand. Do I want to do that? It's really hard to say. Do I want the x-axis, the y-axis to go to 0? I think I do in this case. Yeah, I think I do. It's just going to make this so hard to label these points. And if we don't label these points, it's not going to be a very good graph. So I'm going to go ahead and see how this looks. Here I am going to use geom text repel. And I'm going to say AS label equals, what was it called, major category. Start with that. Yeah, a little too much forced, pushed away. I like a little bit lower. I like to, then I'll zoom in a little higher than that. This is controlling how far everything is moving. Force equals 0.2. You know, it's not a perfect graph. People usually go through it afterwards and mess with it in Illustrator, but it gives a sense. What this looks like to me, and I'm actually going to I am going to throw in a best fit line. Almost anyone who made a graph like this would do so. My first instinct is that what this looks like is engineering and computer mathematics are outliers in two dimensions. They're outliers in higher salary and more men. If we remove them, the correlation would probably be weaker. I can't even tell. The correlation might not even be significant right here. Having said that, there's more we would do for an actual. We might go ahead and do a couple statistical tests now. This was good as a first exploration, but we also notice health is an outlier, unusually high earning, and the highest percentage of women. So we have the question is, if we dropped those. If we dropped these two, the correlation might go flat. If we drop this one, we're not going to drop any of them. I'm just trying to get a feel for what affects this distribution. Maybe still a negative correlation, very hard to tell. If I had done this not on major category, but on major, what would that graph look like? Here is just called median, and I called it majors processed. And I definitely don't want a label on this one, too many points. Here the correlation becomes clear. That's actually something really important, is if you're applying a statistical test, you probably don't want to aggregate first. You don't want to, because if you do, you're going to lose a lot of the information about variation that you have. This will also keep us safer from Simpsons Paradox. So Simpsons Paradox, is it Yeah, so so Simpsons Paradox. Here's a problem. What if it turned out that, let's say, for example, we see that health is the highest share women, but also a relatively high median salary. What we also, though, saw that nursing was among the highest in women and not that high in salary compared to some of the other majors. So it might be that the areas within health that have more women also have lower salaries. That would be correlations within each category that are different than the overall correlation. So that's really worth, that is Simpsons Paradox. And here at least we can see a bit more information about a negative correlation. But we can also throw into that color equals major category. If I were doing rigorous statistical, I do not want one group for every one of those. I want for every line. That's a bit of a mess. This is one way of giving us a feel for what the correlation is and what drives it most. We still have too many categories. All right. We could go about doing statistical testing. That might be the thing to do. Is we can look at a statistical test of just of correlation. Do ones with more women tend to have more meetings? I'm nervous about a lot of it. I'm nervous about the effect of major category. I'm nervous about doing weighting. All right, I'm actually going to try it. All right. What I'm looking at here is which variables are we going to include? I'm going to look at major, for sure, total, always nice, share women, and sample size. Sample size is going to be really critical here, and then median. All right, I want to predict median from share women and see if that's a significant effect. And here's the good news. We get to use sample size as a weighting variable here. We're going to do a weighted linear regression. This means that actually it's not going to pay, for example, this means it won't pay a lot of attention to metallurgical engineering as because it only has 3 measurements going into it. The way we do that is we pipe it, I'm going to pipe it to the LM function for doing a linear model, data equals dot. And there being this data going in there, we're going to say median explained by share women. I'm going to add one extra argument to this, which is weights equals, I believe we can say weights equals sample size. This is a weighted linear regression. Here we go. This weighted linear regression says, would say count this has way more data than this one does. So consider that in the regression. Having said that, it's worth noting that technically weighted linear regression expects this to be a mean rather than a median. This is one thing we don't have the original data, so we can't change how we work with that. But here's my super wonky, nerdy stats major talking. Because the salary data is typically log normally distributed, the median will be close to the geometric mean, and we probably would be doing this regression on a log scale anyway. So it's probably not going to work out not to be too much of a difference. Ran the wrong line there. Here's my regression. Pipe it to summary. Here's my regression. Definite negative effect. The story here is that if you went from 0%, a field went from 0% women to 100% women, it would go, the expected median salary would go down by about 24,000. Put another way, you could say every percentage point that a field is male, the expected salary would decrease by 23 over 100, so by what is it? $200, $300. So that's worth knowing. It's a very significant p-value. Okay. When I often, when I'm working with these, use the tidy function. We're not going to need that here. Or are we? All right. Let's talk about major. Let's talk a little more about Major's process in Simpsons Paradox. One thing we could do is divide down by category. Say, are there correlations within each category? Might be interesting. I'm kind of interested, particular about health. Does this correlation present within just the category of health? But we're not going to be able to do this analysis for ones that have fewer than maybe, I don't know, 10 majors within that category. So I'm going to do some filtering first. I'm going to do it very specifically before I see the resulting p-values. I want to say within engineering, within business, within physical sciences, what is the what is our what is the correlation between share of women and the average salary? That would be one step in the direction of discovering patterns of discrimination, or you'd need to have a lot more work to do. But we could say actually within healthcare, if the more female areas tended to be women, that would tend to have lower salaries. That would be an interesting conclusion to draw. So what I'm going to do is nest this data. I'm going to filter first. I'm going to say add count. That's a verb in dplyr that tells me how many engineering majors are there. 29. It just added an N. How many engineering? 29, 29, 29. 13. Some majors have only 10. I actually don't want to do a correlation if there's only 10 in a field. I'm going to say you need at least 20 observations within your major. Nope, doesn't work. I'm going to bring that down to 10. Ugh, feeling a little sloppy there. The reason it didn't work is that the only thing with more than 20 was engineering. Engineering has a wide variety of majors. How many major categories we have if we limit it to ones with at least 10? I'll change it to a count. Looks like, okay, we have 9 majors. 10 and for each of them we have at least 10 different majors, and we want to say what's the correlation within that major, or rather what's the correlation between them. To answer that, here's where we're going to do some judo. I'm going to nest everything besides major category. Now every one of them is a nested data frame. You can take a great new course by Dima Gorenstein on DataCamp called called Machine Learning in the Tidyverse to learn how to do all these steps, or read the Managing Many Models book. The Managing Many Models chapter of R for Data Science also shows how to do this. And what I'm doing is I'm going to say library Broom. Broom is my own package for tidying model outputs. I'm going to say the model is for every data we want to find. We're going to apply this within every single major category. We're going to say median explained by share women on this data with these weights. Then I'm going to say tidied equals on the model. I'm going to tidy every one of these, turn them into a coefficient, into a 2 data row data frame of coefficients. This is definitely one of the most complicated thing we're going to do today. So if you don't understand it, check out those courses or that book. And here I now get the coefficients within every category, the results of every one of these regressions. The intercepts are interesting, but the intercepts are really about the overall earning within. So we see it's lower in humanities, for example. It's interesting, but it's not what we're looking at right now. So I'm going to filter for the term is the share of women. And I'm going to range by the estimate, the slope, the coefficient. All right. What I see here, I also realize I'm going to need to adjust these p-values. When these p-values adjusted by a method, by the Bonferroni method, none of them will be significant because they're if you're multiplying all these numbers by our 9 categories, this is not going to they all go very high. But if I use false discovery rate control, it might be a bit of a different story. False discovery rate control is adjusting a p-value, not trying to get everything right. It's trying to get only a subset right. So I can use p.adjust. It's trying to say for every single, how are we going to control our overall error rate? Get only a fraction of them wrong. This is much more, I'm not teaching this here, and it's a much more complicated method than I'm giving it credit for. 2 of them fall under an FDR, false discovery rate of 0.1. No, 4 of them do. So basically, if I said all 4 of these have a significant trend, I would be wrong on 10% of them. That is, maybe on 0 or 1 of them. As in 0 or 1 of them would be would be due to chance. So this, I would describe, if I were publishing a paper, I would need to be very careful about this, about my conclusions. But if I were writing an internal report, I would really say there's a strong suggestion that at least a few of these, engineering, business, agriculture, health, I'd say that at least a few of them have negative correlations in terms of share of women and typical salaries, even within the department. That is, that correlation is not just about across all departments, it's also within them. There are much fancier models we could use. Probably a hierarchical or a linear mixed effects model would be the way to go about this this analysis. But yeah, but I won't go about I certainly won't go about doing that right here. I'm also just not very good at them. It's been a while since I studied them. But but here it's certainly looking suggestive that there's negative correlations within departments and not just across them. So that's really interesting. That roughly concludes the time that I wanted to spend on analyses. It looks like we looked at about 3 questions. The first was kind of just an exploring generally one. What are the most common majors and major categories? Here I'd say here are our most common major categories. This one I might have not shown this at all and just shown it broken down by gender, which I didn't. Did I do that? No, I didn't. I did a slightly different graph. I'm getting to the point of the analysis where I'm forgetting what I did and where. That'll happen. We could have done this by major category. You know what? I'm going to go ahead and do that. I think that there's conservation of effort when you're creating graphs. You don't want someone to read 4 graphs if they could get a lot more out of one. Put another way, not every graph is worth 1,000 words. Some are worth more, some are worth less. So if I'm going to show the total number of graduates, I'm going to go ahead and do it at the aggregate level. I'm going to take my by major category data set. I'm going to move it up to the top. I'm going to say this is one of my early data cleaning steps. I would actually mention that. I'd say I'll also be aggregating by category. I probably would say something like that in the resulting blog post if I was showing the code as I go. So then what I would say is here, instead of actually counting, I'm going to do it by total. I'm going to say, take your major category. I'm going to run that same gather logic that I did. Gender, total, gender, number, men, women, and I'm going to say fill equals gender. I'm going to leave the legend in, and I'm going to do the mutate before the gather to ensure that the total has been the same order. And I got a bug. What bug did I get? FCT reorder major. N. It's not called N in this table. It's called total. Back here when I did FCT reorder, I needed that to be called total or not. Gosh. Oh, it's this N down here. I had neglected to rename either of them. That's what happens when you try and reuse your own code too much. All right, so this might be the graph that I would show. Something's up. They really all look like those are all 50-50. I missed something. Oh, anyone see it? Here it is. I was graphing the total when I should have been graphing the number. Be really careful when you make your graphs. Like, if they look weird, dig into that a little bit. All right. Here it is. Business 50-50. We didn't make this plot, did we? No, we made it by major. We didn't make it by major category. I like this plot more because it kind of covers everyone. Computers, mathematics shifted towards men. Engineering shifted towards men. Education, psychology, health shifted towards women. All right, that would probably be my first graph. Heck, I would probably throw the scale y continuous labels equals comma format, I would give this a title like, what are the most major category, and I would probably drop this graph. This is the most common majors, which is like, yeah, I guess it's kind of interesting that Biz Management Administration and General Business are separate but both big. But we really wanted to get a feel for the most common categories. This is probably too much detail. When I have a graph that's too much detail, I either delete it or I move it to the end after a knit exit step, which means this actually wouldn't run. Scrap work. If I ever want to come back to it, I can. I usually don't. But the nice thing about having a scrap section is you're never afraid to cut things out when you're like, I'm not going to make that graph. And now I can get rid of, but this graph I can get rid of. That was a graph of my most common major categories. All right. That's one analysis. Next, I'm interested in what categories of majors make more money than others. I like this box plot. I'm keeping this box plot with only one change, which is I want to say, let's say fill equals major. I'm going to do the funky thing and say fill major category, drop my legend. I like it. I'm into it. I'm gonna thumbs up that. And this is a really interesting conclusion. Oh, I'm gonna make one other change while I'm at it, which is to make the y-axis start at 0. Otherwise, I would really say this is a misleading graph if the y-axis doesn't start at 0. Yeah, feel way better about that. Engineering outlier, other than that, computer, business, etc. Moving down the chain. We didn't look at unemployment at all. But that's okay. Well, maybe next time. All right. Most common majors. No, this is by category. This is median. I like box plot more. I look in between the two. This goes in the scrap. And then I would say, what are the highest earnings? And that's really interesting. That's a relevant one. And remember that I said I did a filter. I said only at least 100 graduates surveyed. We look, and here are 100. Or here are 20 majors. Pretty interesting. If we want to look at specific majors and the specific lowest earning majors. This is the kind I might have just drop if I were writing a blog post, because we already look by category, and the highest majors is fun to know, but like, do people really need to know? Oh, I forgot to do a filter. I want to keep that. If I do that filter for the highest, I definitely have to do it for the lowest. No question there. Yeah, do I really need to know composition and rhetoric has a slightly lower one than drama arts? Plus, they're all just so close to each other. I would probably drop this one. I might drop the other one. I'm going to go ahead and remove lowest earning majors. If someone wanted to get the answer to that, I'd have built them a Shiny app where they could actually go through and explore it, like an interactive visualization. But with graphs, I don't think it's quite interesting enough. That's my choice kind of as a data journalist, as a writer, that I would make at this point. And what was this graph? Oh yeah, understanding the variation. This is more of an appendix graph. This is like, I would actually, yeah, if I were writing a report, I'd put this in an appendix before the scrap. But where I wanted to understand the relationship between sample size and median and see why I picked a limit of, what I do, 100, is that the variation is kind of bigger below that. And then I'd say, how does gender breakdown relate to typical earnings? And I'd look at it by, that's by major. I like my other one by major category more. I might leave that in. I'm not really sure. If I finish writing up, I might decide it fits the flow. It might not. This one is definitely, actually, I might not do it by category. I might have shown the one across all categories. Yeah. You really don't want to give a linear model without showing this scatter plot so people can understand, oh, there's an outlier, petroleum engineering. And having said that, I would drop the color because, nope, I'm not going to drop the color. I take it back. I'm going to lump that color. Those are too many major categories, but just because they're too many doesn't mean we can't show it. I'm going to lump them with the most, let's see. into the 6 most common. Let's try that. Put it back. Let's find out, how does that look? How does that look? Ah, it doesn't. Oh no! Oh, oops! I did it on the wrong graph. I meant to do it on this one. A little bit better. Ah, still too many colors. 4 and other. Here's your engineering. Here's your humanities and liberal arts. There's your biology and life science. It's kind of a neat graph. Ooh, I've got one more thing we can put on this graph. Oh, I feel great about this. We are going to put another aesthetic. Size. So here, I'm going to do it size based on sample size, so we have a feel for which ones we can partly or mostly ignore. So we notice this looks like an outlier. This category up here that has a high share of women, but also a higher than expected salary. But it's absolutely not an outlier. It's this one is it has a lot of it is an outlier, but it's not noise. It has a fairly large share. This is in contrast to this outlier, which has a petroleum engineering we saw before, has a relatively small share. This is going to be a good graph. You know what I would do here? I would do library Plotly. Do I have Plotly? Let's find out. Is this the right category? This is the right graph? This is the right one. I would do GG Plotly. Oh no, it's library Plotly. There it is. I would save this, and I wouldn't in a blog post, but I would in a lot of, I don't really do interactive blog posts. I saved this object. Oh, and I add one thing to the points. I say text equals major. Label equals major. Did that not go through? No, it didn't. I really want to get the major on the tooltip. Because wouldn't that be great? We could say, which one is that? Oh, it's such and such. Which one is this? Oh, it's such and such. Which one is... It's not coming through. It's not really happening for me here. Because it's ignoring it, it's dropping the label. If I put it here, would it help? I'm kind of guessing here. I knew I was going to get stuck on something today. And here it is. How do I get the... I love it. I love it. All right. Fantastic. So here would be a first draft of a final interactive visualization about the question of how does a share of women correlate to the median salary of and a major correlate to the median salary. And we could say things like we notice most of them there's a negative correlation. But we can also, and some things like accounting, and business management administration, those two majors fit on that. There are some outliers. One of them is petroleum engineering, with a relatively small sample size, low share of, very high median. Another is theology and religious vocations. We would have expected from its share of women for it to have a higher salary than it did. This is one of the, I wouldn't say outlier, but are larger residuals. Both of these, forestry is another, have lower salaries than we'd have expected just based on the share of women and no other information. And finally, here's a really neat one. It's nursing. Nursing has a high fraction of women, but also a relatively high median salary. So we're seeing an outlier on the upper side. We could publish this visualization after doing a few more changes. Like I definitely want that x-axis on a percent scale. And that y-axis on a dollar scale. Woo! I've got to label the plots better and everything, but already, ooh boy, yeah, this would be one of the things that communicates data more from our after result of our analysis. Okay, so that. See, earlier I said, well, I'm about done with this, but then I discovered a few more things to work on. That is the data analyst curse, as you always find things you're excited to check out while you're working on it. And our last somewhat complicated analysis that may or may not make it into the blog post, remember, was looking within categories. Again, a mixed effects model or a hierarchical model that had both a term for the general category and for overall would probably have been the way to estimate this. Okay. And work with it more rigorously and scientifically. But yeah. All right, so I can say I spent, I'm not sure exactly, I think I spent a little more than an hour in this analysis, and I think it would take about another hour for me to write up the results. Maybe an hour and a half if I discovered a few other things I wanted to analyze. So this was sort of the first half where I did the exploratory data analysis of this. If I were to do a future work section, I would certainly include examining unemployment. Sometimes you just get into a couple columns and you completely forget about some other ones. I did examining unemployment and fraction taking a job requiring a college degree. That would be really interesting, maybe as a confounding factor, or as something that just has a different impact. The other thing I'd look at is interquartile ranges. So, for example, we notice military technology, the people that graduate military technologies, that might, that might just be one school or something, because we know, and one program, because you notice they're all, like, at least half of them are making $40,000. Yeah, that's a weird one. Oh, but the interquartile range would be P75th minus P25th. And we notice, I can never resist answering a question if I start to pose it. We notice interquartile range is P75th minus P25th. I'm doing great at resisting at not going over time. The P70. Oh, it's mutate. And throw in a filter sample size greater than 100, because otherwise we're going to be looking at the obscure majors. Here's what I said: which have the greatest interquartile range? Physics, computer science, economics, and general engineering and computer engineering have the highest. Those have like a 15 to 20,000. Yeah, like, oh no, pardon me, a 40,000 interquartile range. Those are probably ones where you can either go into academic areas, or you can go into some really high earning ones. So we're seeing, we have higher interquartile ranges for some of them. Having said that, it's also we could look at interquartile range divided by the median, might be a better metric, so it's not skewed towards the higher ones. And then we have our ones that have low interquartile ranges, like 10,000. Those include social work, special, and various kinds of education. This makes a lot of sense. Teachers, especially public school teachers, tends to be a very regulated job with a lot of very similar salaries, like a particularly tight salary band. So we get our engineering, economics, finance, could be going to Wall Street, could be making lots of money. Then we have teachers, which tends to be a similar type of pay scale. So that could have been a whole analysis. This is very me to be wrapping up and suddenly want to answer a question. But yeah. All right. And so then examining interquartile ranges. I may or may not write a blog post on this. If I do, it'll be to accompany this webinar. And if you're interested, you can see what conclusions I drew. Finally, I'd conclude by saying this was definitely a really fun experience. What did I learn from it? Well, I learned to make a lot of bar plots in exploratory data analysis. And you see, really, if you flip through the graphs that I made, you probably see an awful lot of bar plots. I learned that when I'm walking through, I do make a few mistakes. Not as many as I was worried I would make when I started this screencast, but for me this is a relatively elementary analysis. So I can tell you I make a lot more mistakes day to day in my own work. But I can also finally I'd say this is such a good choice of data set for Tidy Tuesday. This is actually my first Tidy Tuesday that I've analyzed as part of the day it comes out, and this was so well chosen. If the others are this well done, I'm going to be really excited to see them. So thanks very much for joining me. I hope you learned a lot. I had a really good time, and I'll see you in future screencasts.